Okay, so the topic is two-stage least squares or instrumental variables. And the reason for this additional method is to deal with what we call endogeneity, or what used to be called in the old days simultaneous equation bias. So we'll talk about that first. What is the problem? How do we fix it? And the old fix is by means of instrumental variables. And then we'll go into the situation where we have, in a sense, too many instruments and how we approach that. And that's where two-stage least squares comes into play. And if you're familiar with this, fine. If you're not familiar with it, it's often the first time confusing between what is an instrumental variable and what is two-stage least squares. They're often used interchangeably, but two-stage least squares is a form of instrumental variable. Instrumental variable estimation is a very old concept and is, in a sense, a little narrower than two-stage least squares. Two-stage least squares is a particular implementation of instrumental variables. And then I'll close with some words about the Durbin-Wu-Hausman test, which is an easy way, not necessarily the best way, but an easy way to assess whether you have a problem of endogeneity with some variables. Because this is a problem in practice. If you have a strong theoretical framework, and historically, this was typically set in terms of a system of equations, a system of simultaneous equations, where you had variables that were determined by the system itself. They were called endogenous variables, and then variables that were outside the system, and they were called exogenous variables. And within this system, you knew exactly what was endogenous and what was not endogenous, so you didn't have to test. We don't have a system. In typical applications that we talk about in this class, we have a cross-section, and we have a bunch of variables that we think are related in a linear sense to the dependent variable. But some of these, typically, very often, are actually jointly determined with the dependent variable. For example, there's often at least a hypothesis of an interrelationship between crime and economic circumstances. So say high poverty, high crime, but also high crime, high poverty. So which direction does our causality go? This is a case where these two variables are determined by the system, and so in a sense can be considered to be internal to the system, endogenous. So if you have crime on the right-hand side of a equation explaining poverty, or the other way around, you can't really treat these as being exogenous. And so this violates, as I'll show you in a second, one of the fundamental assumptions underlying least squares estimation. And so that is the core problem. And in the spatial case, so the problem of endogeneity in instruments, in the spatial case, the endogenous variable will be what we call a spatially lagged dependent variable. And we'll talk about that next, later this week, when I go over the different spatial model specifications. So right off the bat, we have a problem of endogeneity. How do we address that? As I mentioned earlier, in the spatial case, the classic approach is to use maximum likelihood, which is very nice, but has a lot of assumptions behind it. A more modern and a more robust approach, in a sense, is to use instrumental variables or its implementation through two-stage least squares. So what is the problem? We take the general model. Again, just as I did last time, everything is matrix notation. So we have a vector y of the dependent variable. And on the right-hand side, we have a matrix. Remember, I used to call this X, now I call it Z, in general, of explanatory variables with an associated column vector of coefficients. It's a linear relationship, and then the error term. But unlike what we had the other day, some columns of Z are actually correlated with the error term. And recall what I said last time is we want to separate the signal from the noise. So the signal is the X, the noise is the error term. If some of these variables are actually correlated with the error term, then we have a problem. Because then we have two sources of variability. Remember, one of the assumptions we made was that X was not stochastic. And even if it was stochastic, we didn't have to worry about it because there was no connection between the randomness of the X and the randomness of the error term. But if the Z, one of the Z's, is correlated with the error term, then we do have to worry about it. Because then the two sources of variability, the pure one from the error term, and then the one in the Z matrix get mixed up. Okay, so that's the problem. How do we fix it? A very old solution is instrumental variance. So to recap, the least squares regularity conditions that we went through last time is that you can write it a number of different ways. They're actually not equivalent. They're in a strict sense, in a mathematical statistical sense, one is stricter than the other, but for our purposes, we can just talk about it as being not correlated. So there's no correlation between the Z elements of Z and the error term, and that gives us, if you recall, this Gauss-Markov theorem, which shows that among the unbiased estimators, least squares has the smallest variance, has the best precision. So this not only holds in finite samples where we use the expected operator, but also in the limit. And in the limit, we use these other operators. If you've never seen this before, it looks a little weird, but these are probability limits. It is basically using things like laws of large numbers and central limit theorems to prove uncorrelatedness in the limit. Now, the limit doesn't exist, right? It's a mathematical construct. It's to show that something is well behaved if you have enough information. Just like laws of large numbers, the average converges to the mean of the population. You don't know the population, but by taking this mathematical construct, you can show that, in fact, if your sample is large enough, your average of the sample will become very, very close to the average in the population. And of course, if you've never done this before, I really recommend it. You should simulate this. So you should use a random number simulator, simulate a standard normal distribution, so mean 0, variance 1, and simulate 10 of them and compute the average. It's not going to be 0. Okay. If you do 100, it's going to be a little closer to 0. If you do 100,000, it's going to become basically indistinguishable from 0. So that's the law of large numbers, that sample properties, so averages from the data, standard errors from deviations from the data, variances from the data, converge to their properties in the population, which we don't know. In the regression context, it's the same thing. The estimates of the coefficients converge to their population counterparts in the limit if the sample is large enough. And that's where this PLIM comes from, probability limit. Always divide by the sample, because otherwise this becomes infinitely large. So if you, wonder, you see this in a textbook, where does this 1 over n comes from? That's where it comes from. If you don't correct for that, then this product, because there are more and more elements to it, will become larger and larger and larger. So we, in a sense, take an average. So in the limit, this is uncorrelated as well. These are just kind of theoretical things. So the problem is that because this is non-zero, OLS, ordinary least squares, becomes biased and also inconsistent. So this bad property holds both in terms of finite sample properties, but also going to the limit. So going to the limit doesn't help. Oftentimes it helps, but not in this case. So you can figure out this algebra if you care to do so. Essentially, it's because of this, right? If this expected value, what we call the correlation between all the z's and the error term, is not zero, then the expected value of this operation, which is the OLS estimation, is not the same as the population regression coefficient, this delta here. And going in the limit doesn't make any difference because this is non-zero as well. So we have a problem, right? How do we fix this problem? The solution is very old. This is a type of estimator that's been around for a long time, and it's called an instrumental variable estimator. And what I found useful when I initially was confused by this terminology is to remember an instrumental variable estimator is 1 for 1. Two-stage least squares is many for 1. And we'll see in a few minutes how that works. So 1 for 1 means you have an endogenous variable. You have one of these z's. You replace it by an instrument. One instrument for each endogenous variable. And then with that instrument, you do instrumental variables estimation, which has certain properties that give you a consistent estimate. And so you're in business. So we call this matrix Q, just for no, it's confusing. In the textbooks, you find Q, you find H, and sometimes H is used in two-stage least squares, or Q is used in two-stage least squares, and then one of these is the actual instrument. So it can get very confusing. As long as you remember that in pure, if you wish, instrumental variables, it's always 1 for 1. Okay. Two-stage least squares is actually also 1 for 1, but you only get there by converting the many to 1 first. So that's the difference. So this Q matrix has the same dimension as Z. As I said, 1 for 1. The exogenous variables, which we're going to call X, don't need one. They're their own instrument because they're already uncorrelated with the error terms. So we want something that replaces the endogenous variable, doesn't have the bad property of being correlated with the error term, but is not too crazy. So it has to somehow be correlated with the original variable. But here's the catch. It can't be correlated too much, because if it's correlated too much, it again becomes correlated with the error term. So there's this fine, I mean, it seems kind of crazy, right? Why couldn't I get a variable that's really highly correlated with the original one? Well, if it's highly correlated, then it's going to be correlated with the error term too, right? So you have this fine balance, and there's a lot of controversy in the literature and also in practice about picking instruments. It's a big, it's not a science, it's an art. And it has a lot to do with your strength of how you can convince other people to believe that your instrument is a good instrument. Okay. And in economics, geographic instruments are often used because they're clearly, well, not always that clearly, but at least they seem to be outside the system, right? Distance to a river, what does that have to do with unemployment, right? And things like that. You see these kinds of exogenous variables that are then very strongly defended, but sometimes that's more assumption than anything else. It's really an art to some extent, but you can check it. There are different tests to make sure that your instruments are at least uncorrelated with the error, right? That is something that is critical. So if you have that, then you get a good estimator in the sense of consistency, but it's not necessarily very efficient. In other words, it could be on target on average, but it has a huge variance. It's very imprecise. And so as long as you can establish that your instrument is uncorrelated with the error term, you're in business. But that doesn't mean that you have a good estimator in a sense of precision. And so that's where a lot of the discussion about instruments is about, especially in the spatial context. As we'll see later, there are a bunch of candidate instruments, but there are some that are optimal in the sense that they give you the smallest variance. So once we have this instrument, as I said, 1-for-1, we have to make sure, and there's a lot of notation here which you can skip, just think of the main concept, is that you can think of this cross product of Q times Z. So again, using my trick, Z is N by K. So Q also has to be N by K, same exact dimension. So Q prime is K by N. So this is a K by K matrix. It's not symmetric, unlike X prime X, which is symmetric, but it's still a K by K matrix. And we're going to have to invert this matrix. So we have to make sure that it's full rank, and the rank is K. So the rank is the number of coefficients. So this matrix has to be a proper matrix that we can invert. It cannot be singular, which means that you have to be careful with some instruments, especially when you have things like what I call dummy variables. Because dummy variables can sometimes create multicollinearity with the instruments, and then we have a problem. So that's a first property. So think about it this way: if we need to invert this cross product, then we have to make sure that it can be inverted. So we have to make sure that it's not singular, that it has the proper rank, right? And the other one is the same one again. We have to make sure that it's uncorrelated. And uncorrelated, see this plim thing, it's in the limit. Okay, so asymptotically, it's not correlated. And if that's the case, then we're in business, because we can create this new estimator. We have Q prime Z, which we can now invert. We just established that. And we have Q prime Y. This is the original expression of the instrumental variable estimator. It looks a lot like OLS. OLS would have been Z prime Z, Z invert Z prime Y. So this is Q prime Z, with Q mostly being the same as Z. All the exogenous variables are just themselves, but then the endogenous ones are replaced by an instrument. And it's a K by K matrix, the same number of instruments as there are endogenous variables. And you can prove by working this out that it's consistent, and the consistency is established by the uncorrelatedness in the limit of this instrument matrix and the error term. So some of these we already established because the exogenous ones are uncorrelated. The other ones we established by assumption. We say we pick instruments that are uncorrelated. And then the second part, and is getting more and more complicated, I'm warning you. But it's under the hood is very simple. The expressions are formidable, but essentially what this is about is this part is 0 in the limit, so all of this falls away, and we have that our estimate in the limit goes to the correct value. And that's all that this gives us. Doesn't tell us anything about the variance. To do the variance, you have to do a little more algebra, and I will spare you this, but as I warned you, it's getting more and more complicated. So it looks more complicated than it actually is, because these are all K by K matrices. Remember, Q has the same dimension as Z, so this first one is K by K. The second one is K by K, and the third one is also K by K. And what we saw last time is in an OLS regression, we have X prime X inverse, X prime sigma X, and then X prime X inverse. If we assumed classic IID error terms, then the sigma is a scalar, sigma squared, with an identity matrix. So the middle part in OLS case becomes X prime X. These cancel out, and it simplifies to just this first term. With instrumental variables, that never happens, because they're not the same. This is Q by Q, and Q prime Q, and this is Z prime Q, or Q prime Z. So they're not the same matrices, they can't cancel out. So you always have this long string of matrix products, which looks formidable, but they're all K by K, they're all small matrices. So in the classic case, this sigma is just Q by Q. And then just as we've seen in the least squares estimation, we can walk away from this strict assumption of the classic IID error terms, and then we can allow general heteroscedasticity, and we can allow spatial autocorrelation of unknown form. We talked a little bit about that last time. We'll revisit it later using some kernel function to estimate the covariance terms. So the hack variance term. So just like in the OLS case, we'll have white standard errors and hack standard errors in the instrumental variables case. Now, what is two-stage least squares? Two-stage least squares is the case when you have more instruments than endogenous variables. In the instrumental variable, the classic case is 1 for 1. Here we have more. So you have an endogenous variable, and say you have 3 candidate instruments. Which one do you pick? So for an instrumental variable estimator, you need to pick one. But which one do you pick? You can pick either one of the 3 if they satisfy the conditions, if they're uncorrelated with the error term and correlated with the original endogenous variable. But if you can pick any of the 3, then you can also pick any linear combination of the 3, because they also have the same property. So if each of them is uncorrelated, then any linear combination, sum or weighted sum of any of the 3 has the same properties. It also is a. So which linear combination do we pick? And here is where the 2 in two-stage least squares comes from. We pick the one that is closest to the endogenous variable. Let me rephrase this. We pick the linear combination of the instruments that is the closest in a least square sense to the original endogenous variable. In other words, we will regress our instruments. We will regress our our endogenous variable on the instruments, and the predicted value from that regression is the closest to the endogenous variable that we can get from any linear combination of these instruments. Because it's the closest by definition, by construction, if you wish, in least square sense. This is how we set it up, right? And then that predicted value becomes the instrument. So we're back in 1-for-1, okay? But there's an extra step. That's where the 2 comes from. So the extra step is we have too many instruments. How do we pick which one? We don't pick one. We pick the best linear combination of those instruments. Linear because it's the predicted value in a regression, which is a linear combination of the original columns, with the weights being the betas, the regression coefficients. So we pick the best linear combination of these instruments in a least square sense. So the predicted value in that regression is as close to the original endogenous variable as you can get in a least square sense. And I say this, you may say, why does he keep repeating this? Because there's other senses in which you can be close that are not least squares. For example, absolute differences. That's another criteria. And there's a whole bunch of these with different powers of differences, right? But in a least square sense, you're the closest. And so the second step is then again the 1-for-1. We use the predicted value, which is as close as you can get, and by construction is uncorrelated with the error term, so it's good. We use that as the instrumental variable, and that's 2-stage least squares. So everything that held for the instrumental variable that I just talked about also holds for 2-stage least squares, only the expressions get even longer, right? So here we go.
Discontinuity special form of 2-stage least square?
No, discontinuity would be a form of heterogeneity. Is that, you mean in time series, right? That is where there's a break in the relationship. Yeah. Well, I think you can use instrumental variables in that case, but the problem is with discontinuities, and we won't talk about that in this class, we'll talk about it in the winter. Heterogeneity is a structural break. And the question with structural breaks is, where is the break? And is it exogenous or is it endogenous? And that's where the endogeneity problem comes in. You know, do you pick the break from the data, or do you say the break was COVID? And we have pre-COVID and post-COVID. So we have 2 sets of regression relationships really over time. Right? And in spatial case, we'll have a similar thing. You know, we'll have maybe city center and the suburbs, which is a spatial definition of the break. That's an exogenous spatial heterogeneity. Or we'll say, can we determine these regions endogenously? And that's a special application of spatial clustering, but now spatial clustering for the regression coefficients. And that's endogenous, what I call spatial regimes. Again, not in this class, but in the second one. So as I mentioned, the optimal choice is the combination that is closest in a least square sense. And so if we look at this monster here, what does this do, right? There's a lot of Q's in here, and there's Z. So for each column of Z, we have this expression, which is OLS. So this is X prime X inverse, X prime Y. The Y, the role of Y is played by each column in Z. The role of X is played by this matrix Q, where of course the exogenous ones are replaced by themselves. So for the exogenous ones, nothing happens, right? You regress something on itself, the result is a coefficient of 1, right? And so then this is a set of coefficients And if you multiply that by Q, you have the predicted value. So this monster here is nothing but the predicted value that you get when you regress each of the Z columns on all of the instruments. So for the exogenous ones, the regression coefficient is 1, so you just replace it by itself. For the endogenous ones, the regression coefficient is not going to be 1, and you actually have a predicted value, and you plop that in instead of the original Z variable, and then you do instrumental variables. This matrix, this first part, this is not a K by K matrix. This is a big one. This is N by K, K by K, K by N. So this is an N by N matrix. This is called a projection matrix. And you'll see this in the textbooks all over the place. This has a lot of optimal properties. So then we use these predicted values as instruments, and we write the instrumental variable estimation. Remember, we had Q prime Z, Q prime Y. So Q becomes ZP, the predicted values, ZP prime Z inverse ZP prime Y. And with a little bit of algebra, I won't get into that, you can actually show that ZP prime Z is the same as ZP prime ZP. So now we're back into OLS world. There's no more weird cross products that have different symbols. They're all the same. So this at the bottom is an OLS estimation with the same dependent variable Y, but replacing the original Z by all these predicted values. So for the originally exogenous ones, it doesn't make any difference. The endogenous ones are replaced by their predicted value from this extra regression. Hence the term two-stage least squares. There's 2 stages. I mean, in the old days, that's how you would compute it, but you don't have to anymore. The first stage, you get all these predicted values. And then in the second stage, you do the regression with the predicted values. So stage 1, OLS of each of the columns of Z on all the instruments, and that gives predicted value. Stage 2, OLS of Y on these predicted values. Now, there's a slight catch that if you have the residuals, you can't take the residuals from this second regression because this is the wrong explanatory variable. You have to get the residuals from the original Z. So if you do this by hand, and in the notebooks, we'll do it by hand, we'll do the actual 2 stages, then you'll see when you compare the results of the actual 2-stage least squares in terms of standard errors to those of the second stage, they're not the same because the residuals are different. The naive way, as I call it, is get the residuals using the predicted values on the right-hand side. The correct residuals use the original endogenous variables on the right-hand side. Okay. And then here's my favorite monster. Do you have a question?
Yeah. Around each of the columns of the matrix, does that mean the columns are sort of there's like a collinearity issue between among columns?
No, there's so you take Z, let's say you have a constant and you have 3 variables, right? Constant remains the constant. The first variable is exogenous, So if you regress that on the other exogenous variables, all the exogenous variables and the instruments, the coefficients of the other variables will be 0, and the coefficient of itself will be 1. So you might as well not do it, right? However, when one of the z's is endogenous, that will not be the case. Okay? Whether it's multicollinear or not is actually a separate problem. Okay, but intrinsically, there's no problem with multicollinear. Okay. Now, you know, this looks formidable, but all we've done is replace our instrument by what it is. This is the instrument. So if you love matrix algebra, you just do our, you know, Q prime Z, Q prime Y, Q prime Z inverse Q prime Y, plug this into what the earlier Q was, and you end up with this nice expression here. Okay. To remember, Z is everything. It includes the endogenous variables. Q has all the instruments. So Q can be larger than Z. Okay. Doesn't matter, because in the end, this makes sure that it's square. Did you have a question? Okay. So if you do all the dimensions, okay, Z, I'll just do it once, right? Z prime is K by N, right? Q is N by whatever. Let's call it M, right? M is the number, the original exogenous ones, plus all the instruments. So M is not necessarily the same as K, but this is a, you know, this is square again, M by M. And here we have the M by N by K. So we're back in K by K. Okay. So it all kind of works out. And then the asymptotic properties are the same as before. We have the instrumental variable. Yeah.
Time, but like denote transpose.
Yes. Yeah. Yeah. So if Z is N by K, then Z prime is K by N flipped. Yeah. Yeah. So, you know, you see the monster. This is it, but it has the same basic structure as before. You just replace what we had as the instrument by this full matrix expression, and then it just gets bigger and bigger. Same as before, we have this sigma in here, which we can assume to be sigma squared I, which is the simplest case, or we can make it heteroscedastic, or hack as the form. Right? One kind of subtle thing, but depending on how picky your advisors are, you should know this, that the properties come from special laws of large numbers and central limit theorem. So a law of large numbers is about averages converting to their population means. And these averages also become the estimators. So estimators converging to their population values, because you can express most estimators as some kind of complicated average. And so then we're in the same business. Those are laws of large numbers. Central limit theorems are a little more complicated, and they show asymptotic normality. Now, this is, and most of you said you were not familiar with asymptotics. This is a bit of a mind game, because when I say an estimator is consistent, what does that mean? It means that in the limit, you get the population value, right? So you try to estimate a coefficient whose true value is 2, And if your sample is large enough, your estimate should be 2, right? As I said the other day, the coefficients in classical regression analysis, the regression coefficients are constants. Does a constant have a distribution? No, it's constant. So how can I talk about asymptotic normality? It doesn't make any sense, right? In the limit, there's no normality. Because it's consistent, you're with a constant, you're stuck. So this is a kind of mathematical trick to be able to do inference when you don't have an infinitely large data set. So when you have an infinitely large data set, you don't need inference because it should be the actual constant from the population, right? But we're not there yet. We say have 100 observations. So we're on our way to the limit. So we're not on target yet. We're around the target. How are we around the target? So these central limit theorems show how the distribution of the estimator suitably transformed is a normal distribution. Well, typically you see these things, we'll see them later. Square root of n, and then the difference between the estimator and the true population value, that follows a normal distribution. So it's kind of a misnomer, and you really have to think about it a bit. You know, if you have consistency, in the limit, there is no distribution. So it's not about, even though it's called asymptotic normality, it's not about having normality in the limit. It's about having normality as you go to the limit. You know, and that normal distribution will have a variance that becomes smaller and smaller and smaller as you get closer to the limit. So in the limit, it actually is not a distribution anymore. It becomes a constant, which it should. Okay. So if you're nowhere near the limit, you might have quite a bit of variability in that estimator, in that estimate, actually. As you get closer to the limit, there is less and less variability. Okay. So this is how we get these properties. We won't worry about that in this class. Just that explains why when you do the regression, you get these asymptotic t-values, just like you do in a standard OLS regression. The big difference is that in OLS, these are finite properties. In two-stage least squares, these are asymptotic properties. So they're really based on getting large samples. Okay. Now our Durbin-Wu-Hausman test, which I like a lot because it's actually one example of a much larger family of tests. But the Hausman tests, there are several types of Hausman tests. But the principle is very nice. And this is a principle that you will encounter in a lot of tests. The point of departure is that you get two equivalent estimators. Under the null, in the ideal circumstance, meaning no endogeneity, we can use OLS, we should, but we can also use two-stage least squares. There's nothing wrong with that. The problem is it's not as efficient as OLS, because we just established last week that among all the unbiased and also the consistent estimator, OLS is the best one. So there should be a difference between the two. And the second one should not be as efficient. In some cases, it's not even consistent. So the null hypothesis is that the two are the same. When there is no problem, when there is no endogeneity, you should get the same estimator by OLS and instrumental variables, or two-stage least squares. The difference between the two will be in their precision, in their variances. And that's what you exploit to set up the test statistic. Okay, so this is way too complicated for our purposes. As it turns out, there's a nice little trick where you augment the regression. And this, again, is an example of a large family that uses this kind of principle for testing. You have the base regression, and you stick some additional variables in there, and then you run a regression, and the test really boils down to checking whether the coefficients of those extra variables are zero. Because if they don't matter, then they should have zero in the regression. And that's easy to test. So how do we do this for endogeneity? We create an augmented regression where we stick our predicted values. Remember our endogenous variables? We run a regression of each endogenous variable on all the instruments. We get a predicted value. If there is no problem with endogeneity, this should not matter. All the explanation should be done by X beta. There is no reason why these additional variables add anything to the equation, right? In other words, we want to check whether this gamma coefficient here is zero or not. If it doesn't contribute anything, that coefficient should be zero, right? So we, under the null hypothesis, no endogeneity, no problem with OLS. We don't need any instruments. If we put them in there, they don't help. They just become the same as noise. They get zero as coefficients. Okay. So same thing, if you have a regression, and let's say you throw in 10 variables because you really have no idea what's related to one, a typical approach, not necessarily the best one, is kind of a stepwise regression where you look at the ones that are not significant. In other words, you decide that their coefficients are not different from zero. So they have a zero coefficient, you drop them. You don't need it, right? And so that's the same idea here. If these instruments, these predicted values, do not contribute anything, then you can drop them. Then you don't need them. Then there's no endogeneity problem. On the other hand, if they do contribute, then you have a problem on your hands. So the test boils down to testing the significance of these coefficients. I say coefficients because there could be multiple endogenous variables. If there's only one, it's easy. It's just a t-test. But if there's multiple, it's a test on the joint significance of the coefficients, and that's an f-test. Okay. That's very easy to do. You run this auxiliary regression, and then you do the significance test. Okay. So that's, at this point, all I want to say about instrumental variables and two-stage least squares. It is the basis for what I call modern estimation of spatial lag models, and we'll return to that later.